Hello everyone and welcome to water electrolysis. Our world still depends on fossil fuels releasing huge amounts of carbon dioxide into the atmosphere. The planet is warming fast and renewables alone cannot meet the demand without efficient storage. That's where hydrogen comes in, bridging renewable energy to a cleaner carbon-free world through water electrolysis. Water is composed of hydrogen and oxygen, two elements that can be separated using electricity. When electric current passes through water, hydrogen forms at the cathode and oxygen at the anode. This process converts electrical energy into chemical energy stored in hydrogen gas. In modern systems, ion exchange membrane keeps the gases apart while allowing ions to flow efficiently between electrodes. Currently, there are four types of water electrolysis technologies.
Let's take a look at the two classic electrolysis technologies, alkaline and PEM. Alkaline electrolysis is the oldest and most established method. It's mature, low cost, and reliable, but its slow response makes it less ideal for fluctuating renewable sources. PEM electrolysis, in contrast, is newer and more compact. It reacts faster, which suits dynamic operation with wind or solar energy. However, it's more expensive because it requires noble metals and costly materials. Both systems split water into hydrogen and oxygen, but ion transport differs. In alkaline electrolysis, an alkaline solution like potassium hydroxide is used, and hydroxide ions move through the diaphragm. In PEM electrolysis, a solid polymer membrane is used and protons pass through it. Thanks to this solid membrane and the absence of liquid electrolytes, PEM systems deliver very pure hydrogen, quick starts and high flexibility, while alkaline remains the cheaper, well-proven option for large-scale production.
Now that we've covered PEM and alkaline electrolysis, let's look at two emerging technologies, an ion exchange membrane electrolysis and solid oxide electrolyzer cells. SOECs use steam at 500 to 850 degrees, making the reaction more efficient and enabling use of industrial waste heat. At the cathode, steam is reduced to hydrogen and oxide ions. These ions pass through a solid ceramic electrolyte to the anode, releasing oxygen and electrons. SOECs offer high efficiency, but the extreme heat causes material stress and limits durability, which still hinders large-scale deployment. AEM operates in an alkaline environment using an anion exchange membrane. At the cathode, water splits into hydrogen gas and OH- ions. These ions cross the membrane to the anode, where they form oxygen gas and water, completing the circuit. It allows non-noble metal catalysts like nickel and low concentration of KOH, reducing cost and improving safety. But it has drawbacks: membrane degradation, low current densities than PEM, and limited long-term stability. Improving membrane connectivity and durability is still a major challenge.
In 2020, the hydrogen factories were in an order of only megajoules, while currently there are factories being built in an order of gigajoules, so-called gigafactories. The most common methods are PEM, alkaline and SOEC. Common transportation methods also have been changed, with pilots being done with hydrogen buses, while mainly in Europe other regions have been testing it as well. Even two commercial car models are now already running solely on hydrogen, the Hyundai Nexo and the Toyota Mirai.
What's really holding green hydrogen back? Three big hurdles: efficiency losses as heat, corrosion that cuts component lifetimes, and poor ramping with renewables. Then there is the cost. Pricely noble metal catalyst and a high electricity share make it expensive. The solutions: using earth-abundant catalyst, smarter membranes, and more efficient system design. That's how green hydrogen becomes affordable and the technology moves forward. Thank you.